Welcome to Electrostatics. Whoa. Okay. So, curriculum stuff. Explain electrical interactions in terms of the law of conservation of charge. So you got to know what the law of conservation of charge is. Explain electrical interactions in terms of repulsion and attraction. Compare the methods for transferring charge, conduction and induction, two terms that you need to know. And explain qualitatively the distribution of charge on surfaces of conductors and insulators, and perform an activity to demonstrate methods of charge separation and transfer. So some history when it comes to electricity. So electricity comes from the Greek word for amber, which is electra. And Thales observed that when amber was rubbed, it attracted small objects. So that's where the idea of charge came from. William Gilbert found that rubbing objects other than amber would also attract small objects. Charles François de Cisternay-Dufay found two types of electricity. So if you rubbed rubber and a glass rod, they both became electrified, attracted a piece of cork. But after touching each piece of cork, they would repel the rod, so they have the same charge, yet the two pieces of cork would attract each other, so different charges. So we found that there's two different types of charges. Ben Franklin took it a step further by describing electricity as a fluid that was exchanged in rubbing or contact, which sounds kind of gross. When two objects are rubbed together, one gains excess, the other becomes deficit, and electrostatic forces of attraction are due to opposite charges trying to become neutral. Okay, so electrostatic forces of repulsion are the objects not wanting to take on any excess charge. So if we have, I forgot I did that. So if we have a negative charged object here, and we have a negatively charged object here, they don't want to go near each other, right? Because they're just going to give each other excess charge. But if I have a positively charged object, right? This guy can transfer some of those negative charges to it, so they're attracted. So they don't want to become more negative than they already are, but if they're opposite, they'll attract. If they're the same, then they're going to repel. So the law of conservation of charge is electric charge cannot be created nor destroyed. The quantity of positive negative stays the same before and after. And just a weird thing, but neutral is not a type of charge, so neutral is neither positively or negatively charged. So I'll show you an example of this. So two objects are separate. They are brought together. Draw the charge of the objects after they are separated. Okay, so these two objects are brought into contact with each other. Okay, so they share this whole big charge when they're brought into contact with each other. So there's 1, 2, 3, 4, 5, 6. After they are separated, right, some of the charge will move into here. After they are separated, they're going to share the charge. So they're each going to have 3. So this was -6, and this was 0. After they're brought together, they sort of share the charge. They're separate. This is going to be -3, and this is going to be -3. Okay, pretty easy law of conservation of charge. So if I have a positive and a negative, they're going to attract. If I have two positives, they will repel. Two negatives, they will repel. We all knew that. So conductors versus insulators. Conductors are objects that allow the charge to flow throughout. So if I had like a negatively charged object here and I touch this together and I charge this up, what's going to happen is this would become negatively charged. And how those charges would distribute would be like this. They would enter, these are all negative charges, and they would try to get as far away from each other as possible, so they would sort of go around the outside. An insulator doesn't allow charge to flow very well. So this is, for example, wood or plastic. So if I charge this up, all my charge would stay in this one little area. Okay, and it's important to know that only electrons move when you're charging things up. Protons do not. So there are three ways to transfer charge: friction, conduction, and induction. So these are the three ways that we're going to talk about. So we can watch a Family Guy video that shows this very well.
I have never been more comfortable as a person than I am in these feety pajamas. All warm and furry. This is what it feels like to be a bear. You remember what I used to say, Lois, when we first got married? You remember? I used to say, what would it feel like to be a bear? Well, this is it. This is it. I'm living it, baby.
No, you're not. You've been wearing those things for 3 days. You can wear them to bed, but tomorrow we're getting rid of them.
Fine. Screw up all my fuzziness. Ah! What the... Ah! Oh, my God. Lois, don't get alarmed, but I think I might be...
Peter, that's a static shock. Your pajamas created a charge of electricity when you dragged your feet across the carpet, and when you touched Chris, you passed it on.
Kneel Ah!
Dad!
I am not your dad. I am Electric Man. Ow!
Peter, I know you're in here.
Yes, I am, Lois. But where?
Peter, if you shock me, I swear to God I'm leaving you.
You'll have to find me first, Lois. Where could I be?
Well, there's a Quonset hut that I've never seen in this room before. I gotta figure you're in there.
How do you know, Lois? I could be in that New York-style magazine kiosk.
Peter, this all looks very expensive.
Yes, you might say it was shockingly expensive.
I'm gonna try the Quonset hut.
I was in the bathroom. The hut and the kiosk. Decoys, Lois. Decoys!
So why do things get charged up? Well, different substances have a different affinity for electrons. And affinity just means how much you like electrons. So for example, rabbit's fur doesn't like electrons, but likes to get rid of its electrons. It becomes very positive. Teflon likes having extra electrons, so that it becomes very negative. It's just a property of the substances. So when rubbing two objects together, the object with the greater affinity for electrons will become negative, and the other object will become positive. So what happened when Peter dragged his feet across the ground? Well, what's going to happen, those are Peter's feet. Right, there's positive and negative charges. Sorry about it jumping around there. It just does that. I don't know why it does that. So we have positive and negative charges, right? And then the ground, the carpet, has positive and negative charges. So either his pajamas had an affinity for electrons, and if that was true, those negatives would move in there and he'd become negatively charged. Or the other thing that could happen is that the ground could have the higher affinity for electrons, and what happens is those electrons go into the ground and he would become positive in that situation. So one becomes positive, one becomes negative. So let's take a look at this simulation. So we have these balloons here, right? And we can see who has the greater affinity for electrons. Well, obviously the balloon does. So when I rub the balloons on the sweater, the electrons go into the balloon because the balloon has a higher affinity. Why don't they spread throughout the balloon? Well, it's obviously an insulator. It's like a rubber type material. It's a plasticky material. So it's an insulator, so the electrons stay sort of where they were. So is the balloon going to be attracted to the wall? So you can see it's attracted to the sweater, which makes sense because the sweater's positive, the balloon is negative. But the wall here is neutral. So is it going to be attracted to the balloon? Well, let's take a look. So as I move the balloon closer, what do you notice happens in the wall? Look at that. So it seems to be repelling all those negative charges. So now when I'm nice and close, the side closest to the wall is positive, the balloon is negative, they're attracted to each other. Right? And through this whole time, you'll notice that the positives never move. It's just the negatives moving around. So So those are all those questions there. So when a charged object is brought close to a neutral object, you can make this charge separation. So a charge separation is induced. So I can show you this charge separation. So this charge separation is just when I take, so I can take an object like my balloon here, and I can take some rabbit fur, ooh, trying to get on screen, there we go, and just rub the rabbit fur onto the balloon. And this little guy right here, this is an electroscope. So what an electroscope does, let me just bring that up a little bit. What an electroscope does is an electroscope lets me see charge. So here there's two tiny leaves that can get charged up. And when I bring the balloon close, right, you can see what's happening to those leaves. They spread apart. They get further and further apart. And then I bring it away. They go like that. So this is charge separation, what's happening right here. So charge separation, I can explain what's going on. So right now, this is neutral, right? There's equal positives, equal negatives. So the leaves lay sort of limp. And then I take an object like my balloon that could have a negative or a positive charge. It doesn't matter, I can show you both. So those positive charges stay where they are. But all these negatives here, what they're going to do is they're going to be repelled. They're going to move into the leaves here, which makes the bottom of the electroscope negatively charged, the top positive. And it makes those leaves spread apart. Okay. So if let me just clear the ink on here. So if I brought a positively charged object close by, right? Those positives would stay in the same spot, but now my negatives would be attracted to the positive end, which would make this positive, and the same thing would happen. My leaves would move apart because the leaves would be positive, and then they'd sort of spread apart like that. So that's charge separation. Okay, nothing touched. Charging by conduction is when objects of two different charges are brought into contact. Electrons will flow from the more negative until a balance is obtained. And then after this, both objects will have the same charge. So I can show you that. So let me bring this guy up again. So I'm just going to charge up my balloon. So I charge up my balloon with the rabbit's fur, and I bring it close. I induce a charge separation. And then if you listen, there we go. And I touch it. Come on, come on, charge up. There we go, that's pretty good. So you can see that it's charged up. They're permanently spread apart. I no longer have the balloon anywhere near this, but what has happened is it's charged up. So I can explain what's happening here with my little electroscope diagram. So in this situation, I have a negatively charged object, and I bring it close enough and I touch it to it. And you can hear the little spark when I touch the balloon to the electroscope. So at the start, it was neutral, right? But now, since this has a really, really negative charge and this is neutral, some of these negatives will flow onto here. So what's going to happen after is those positives will stay the same, but now this will be filled with a whole bunch of negative charges, and those leaves will spread apart, right? So in this one, it's actually become negatively charged, right? With this charge separation here, nothing's negatively charged. They just redistribute, and nothing is positive, nothing is negative. This is technically still neutral after they just distributed differently to make those leaves spread apart. In this one becomes negative. If I touch it with a positive object, right, all the negatives will go into the positive object, and well, let me draw that out. Let me show you what happens if I do a positive object. So if I have a positive object and I touch it, those positives still aren't going to move, right? I have my negatives here. Well, my negatives are going to be attracted to the superpositive object, and they're going to move into this rod here. So afterwards, I'm just going to be left with a bunch of positive charges, and then this is positive, so this will spread apart. So that's charging by conduction. Conduction means contact. So grounding is a process of connecting a charged object to the earth. This allows excess charge to leave the object. Grounding will neutralize a charged object, and this is a symbol for grounding right here. So I can show you on my electroscope, so you can see it's still charged up, right? There's excess electrons inside of there. So I can ground it simply by just touching it. I'm connected to the ground, my feet are connected to the ground, and when I touch it, you can see it loses all of its charge. So all those electrons went into me, went into the ground, and now they are gone. So this last one is called charging by induction with grounding. So I want you to take a close look at it. This is going to be tricky to do by myself. Okay, so I'm going to try this by myself, which is a little bit tricky. So what I'm going to do is I'm going to charge up my balloon with my rabbit's fur, get it nice and charged up. And I'm going to bring my balloon close, induce that charge separation, and then I'm going to touch it, and then I'm going to remove myself, remove the charged object, and look at that. It looks like it's charged up. So they're more spread apart than they were before, which is wild, but I never actually touched it, right? So I'm going to get rid of that charge. They stuck together. There we go. And now I'm going to switch up the order, because the order is very important. So if I charge up my balloon again, I bring my balloon close, I touch it, and then I remove myself. Wait, no, that was the order I did before. Sorry, let me try this again. So I bring my balloon close, induce that charge separation, I touch it, I remove my balloon, and I remove myself. You can see the leaves are still pretty much the same. Nothing's happened. So let's try to do it in the right order this time. So I bring it close, I bring it close, those leaves spread apart, I touch, okay, remove myself, remove the ground. It's not working anymore, try that again. Bring it close, there we go. Touch, remove myself, remove the charge, there. And they're a little bit spread apart. So we can see something different is happening. So we'll go through and explain what is going on. So you need to bring an object close to induce a separation of charge. Then you ground the neutral object, remove the ground, and remove the charged object. This is a really important part of it. Okay? You need to do it in this order. So what happens is we have our electroscope. So this is our electroscope right here. Positive. Let me just, no. Positive, 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 negative, negative, negative. So what we do is let's bring a negatively charged object near it, right? And what's going to happen if we bring the negatively charged object near the top, it's going to force all those negatives down into here. So the bottom becomes negative, the top becomes positive. Okay. And then what we do, sorry, this is tricky to do. So this is our negative object. So we have positive, 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 but all our negatives are hiding down here. And then we ground it, right? these negatives want to get as far away as possible. Now they're like, oh, let's go in here. If we go in here, then that's going to be as far away as possible. So all the negatives actually leave the electroscope through the ground. Okay? You remove the ground, you cut this off so they can't get back in, and then you remove this, bring that away. What happens is, well, all those negatives left, so you have a positively charged electroscope, and they can't get back in. So the charge is opposite with this induction with grounding, so which is different than conduction, where you end up with the same charge. Okay, this is your homework. Give it a go. There you go.